And greenhouse gases are on the rise. Carbon dioxide, which is the most concerning greenhouse gas for us, has been steadily rising. According to the Keeling curve, we have a record of at least since the 1950s. Using ice core data, we can actually go back even further and see that we have seen a pretty steady rise since the mid 1800s. And then methane itself, which comes from burping, farting cows, and people are eating more beef, has also seen a nice big bump, a nice big increase in concentrations. Now, the concern in particular with methane is 20 to 30 times as potent as carbon dioxide. What that means is that one molecule of methane can absorb the same amount of heat as 20 to 30 times as much carbon dioxide. And I just want to quick disclaimer here. The reason why I don't give a set number here is depending on the textbook you read, depending on the person you talk to. I've heard 20, I've heard 21, I've heard 25, I've heard 27. But the range has pretty much always been 20 to 30. On a quiz, I would not make you say 20, 21, 22, 23. I'm mean, but I'm not that mean. Now, methane and carbon dioxide aren't the only two greenhouse gases in our atmosphere. Water vapor and ozone are also present, as well as nitrogen dioxide, and there are many other greenhouse gases. Here's the thing. Most greenhouse gases are very, 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 very scarce in the atmosphere, or they don't hang out for long. Nitrous oxide in particular, or nitrogen dioxide, I always get that one messed up. There's also N2O. But nitrogen dioxide actually reacts out with sunlight every single day to produce ozone. Ozone is actually a greenhouse gas near the surface of the Earth. However, ozone here near the surface of the Earth is a very unstable atom, meaning that over time it quickly decays into just molecular oxygen. So we don't worry as much about ozone. There are days where we have more ozone than other days. Usually those are bad air quality days. But in general, we're not super worried about ozone's greenhouse effect. Water vapor, yes, water vapor is also a greenhouse gas. However, water vapor actually condenses almost as quickly as it gets put into the atmosphere. Water vapor is very much here today, gone tomorrow. Don't believe me? Wait till the next time you have a bad hair day. Those are days where humidity is really high, and that's because the amount of water in the air is also really high. So at the end of the day, the two that we're really, really worried about are methane and carbon dioxide. This right here, I know that you kind of feel like a deer in the headlights looking at this, but don't worry, I'm going to walk you through it right now. And there's not really a whole lot I want you to get from this other than just looking at the effects of each of the individual gases on the atmosphere. See, I knew I messed up the formula for nitrous oxide. We go back to that. N2O. Sorry about that. No refunds. Just kidding. No, I always mess up chemical formulas every so often. I took chemistry once in college and barely got a C. But that's okay. Most of what I do is physics. But anyway, so here's what's going on with this chart here, this weird looking graph. Wherever you see these spikes of gray, that represents areas of absorption. Our x-axis represents wavelength. Our y-axis represents percentage of absorbed, percentage of that wavelength absorbed. If you notice, nitrous oxide doesn't really absorb anything in the short wave. So visible light's right here, ultraviolet's back here, near infrared's right here. It's not until you get well into the infrared portion that you begin to see some absorption. And that absorption occurs particularly at 5 and 10 micrometers. Ooh. I will try to edit that out in post, but I want to get this up quickly, so I probably won't. So just say bless you. Sorry about that. Sometimes you just can't control sneezing. So with that being said, so at 5 and 7 micrometers, methane is particularly absorptive at 4. Oops, that's a poorly drawn 4 and 7 micrometers. Ozone, if you notice, ozone's very absorptive over here in the ultraviolet area. That's actually good news because that's actually how our ozone layer works. But it's also very absorptive right around 10 micrometers. And then water vapor has a whole plethora of different wavelengths that it absorbs. And then carbon dioxide does as well. Now, adding this all up, here's what you get down here. This is the atmosphere's absorption spectrum. Let me explain what's going on here. So wherever you see purple, once again, that means absorption. Wherever you see gray, ignoring the rainbow, that is transparency. So if you notice, our atmosphere is relatively transparent to incoming sunlight, which is once again a good thing. However, most wavelengths of infrared radiation are absorbed by our atmosphere, with the exception of this big dip right here, between approximately 8 and 13 micrometers. This is what is referred to as the atmospheric window. Most wavelengths, with the exception of right near 10 because of ozone, most wavelengths are actually allowed to just escape into space during this time. They're allowed to escape into space during this time. In that case, Earth, this is one way that Earth is able to give off, to lose some heat, so it's able to maintain that mild temperature. Now, something I saw on Facebook once when talking about greenhouse gases, this was from a friend of a particular political party that I'm not going to talk about, Republicans. Sorry, who posted this, and basically it said Mount Agung in Bali has just spewed more greenhouse gases in a few minutes than all of humanity in its existence, than all of humanity since the beginning of time. No data, no information, no anything. And yet people commented, yeah, preach it. Well, let me preach something. That's not accurate. Why? I have data. So the U.S. Energy and Information Administration, this is one of the top bigwigs about energy and greenhouse gas emissions here in the United States. In 2007, they estimated that total fossil fuel related greenhouse gas emissions totaled right around 29 billion tons a year. That's a lot of greenhouse gases. 29 billion tons a year. Whereas the total volcanic carbon dioxide emissions on a yearly basis range between 65 million tons a year to 319 million tons a year. Well, let's be generous. Let's use the upper bound. Let's use that more generous estimation. Well, Earth or humans emit 29 billion. Should I get this right? 29 billion tons a year. And then volcanoes emit 319 million tons a year. Let's do a ratio here. So let's see. These zeros go away. So 29,000 divided by 319. I will use my calculator real quick. Okay. So, sorry, 29,000 divided by 319. 90.9. 09090909009. I assume it keeps going, but 90.9. So (90.9) times as much. So we as humans emit 90 times as much carbon dioxide than even the highest amount of volcanic activity. Let that sink in. We humans are the single biggest source of carbon dioxide emissions on this planet. The single biggest source. We emit more than volcanoes do. Now, I guess I'd say, actually, let me disclaim that there's other elements of the carbon cycle that are also responsible for emissions, but those also have natural processes that take that carbon dioxide back into them. Whereas humans, we're spewing way more than most natural processes. So the reality is that we are chucking a lot of carbon dioxide into our atmosphere.